So today we'll continue our lecture series on LLMs and tools. So today we'll start this new topic called Agentic Workflows. So far we've been looking at how LLMs use tools and how they can leverage the benefit of tools in addition to the reasoning ability they already have. And we also saw how external tools can be provided during inference time and the model can still leverage it. So now we'll be looking a bit into what is called agentic workflow. So I'll discuss what is agentic workflow and some very popular papers from this particular field that initially set the tone of this field, right? Yeah. So these agentic workflows are going to be the basis for how people started to build or people started to automate complex tasks that people typically do. And these are now commonly referred to as AI agents. Like first, let's define what agentic workflow is before getting into the details. So to do that, I think it's easier to sort of differentiate between agentic and non-agentic workflows. So there was this YouTube video by Andrew Ng, which sort of initially set the tone very well for this particular term. So what he refers to as non-agentic workflow is like similar to the auto-regressive behavior of LLMs. So when you give it a task, let's say your task is write an essay about IIT Delhi, right? So then what would an auto-regressive model do? It would start generating one token at a time from the beginning of the essay till the end of the essay, right? So in one go, it will generate the entire essay, right? So that is what is referred to as non-agentic workflow. And what is referred to as agentic workflow is that rather than doing it in one shot, maybe first you would define multiple different subtasks in writing an essay. One subtask would be just writing the outline of the essay, right? Not the entire essay in one go. Then after you write the outline of the essay, maybe you will decide, okay, these topics I'm comfortable with. I know what these are and I can write them. But these topics in my outlines is not something that I'm very comfortable with. So probably I'll do some research on my own, probably using the web or by reading books, and then you understand them. And then you write first draft of each of the sections. And then you would read them again from first to the end, and then you realize, okay, some things are working, some things are not working, the flow is not right. Maybe after I write the fifth section, I realize the first section, I should have pitched the introduction better, right? So again, you revise your draft and then you keep doing this on and on until you're happy with the essay, right? So this is an agentic workflow where you don't do things in one shot, but rather you divide them into however it makes sense for you, and then iterate over it multiple times before you say that I'm done with the job, right? So the same thing, what they say is like if you directly use an LLM to generate an essay, then it's zero shot or non-agentic way of doing things. But if you yourself, or if there is an automated way in which you can tell the LLMs that first I'll give you this prompt, you generate the outline of the entire essay, and then I will send you each topic at a time. You tell me what information you know about it and whether you need additional information or not. And then you give it probably the web search tool, saying that, okay, in cases where you need more information, search the web using this tool, figure out more information. And then you ask it to write a first draft. And then you have some sort of a mechanism where it looks at multiple subsections and then reviews it, right? And then finally ask it to polish the entire essay again, right? So this is the difference between agentic and non-agentic workflows, right? Make sense? Look at a concrete example of how the performance of popular LLMs are on agentic and non-agentic workflows, right? For that, let's take this example of human eval. This is a coding dataset where the input is a description of what the model is supposed to code, and it also gives an outline or a function definition of what this function should look like. The model should fill up what is in the yellow part, which is the actual meat of the function, right? And once the meat of the function gets filled up, then this particular data set, for each example, they have some executable unit test cases. So if the generated code is successful, if all the test cases pass through, right? So that is a setup. This was generated by humans, and it was a pretty good data set, and it is used even now for measuring LLM's ability to do coding. So in this setup, let's see how agentic and non-agentic workflows perform, right? So here zero shot is that you give it the description of the task, and then you give the problem that it's supposed to solve. The model should generate what is in the yellow, right? The meat of the function. So GPT 3.5 has about 48% accuracy on it, and GPT 4 has 67% accuracy on it. So these are the non-agentic way of solving the task. And then a bunch of all the other techniques that are on the right are agentic way of solving the task, where you just don't generate the solution in one shot, but you divide them into subparts, or you have certain other components which will reflect on its own output, and then finally it will iterate through multiple cycles and finally say that I'm done, now you can evaluate the code, right? So Intervenor is one such example where, like, there are two specific prompts. One is called the student prompt, which is in the box A, and there is another prompt called teacher prompt. The student prompt is just given the problem description at hand and asked to generate the code for it. Or if the teacher has given some feedback, then in addition to the problem, it takes the teacher's feedback as well and generates the code. And the teacher, of course, the goal is you have access, so you have the ability to run your code, and then you see how the code performs, and then based on the error messages it receives, the teacher will critique like what went wrong in this process, like how should the code have been better generated, and then that feedback is fed back, right? So there will be a point where the teacher says it's good, or just the environment will give you a signal saying like all good, right? So in those scenarios you will stop, and then you will measure the performance of the code after the loop, right? So as you see that it took about like one iteration of GPT to increase the accuracy from 48 to 67%, right? About 20% jump. But rather than doing it in single shot, if you just let the model like iteratively design the solution, then you see you can already achieve somewhere north of 70%, right? So the advantage of agentic workflow is that at the cost of running more inferences, you will end up getting way better accuracy than what you would get if you run just the model once, right? So you can always trade off. So this is a good trade-off, that if you want to choose accuracy, you would build a solution that is more agentic in nature, and if you want to save cost, then you will try to reduce it further, right? So in addition to this, there are also other advantages, in the sense that let's say that you don't have enough hardware to host a very big model, like 230 billion model or 540 billion model, and you only have like the GPU hardware necessary to only host a 32 billion model, right? So in that case, it's better if you generate an agentic approach. Maybe you may get similar accuracies as a big model, because for a smaller model you can run it iteratively multiple times, the cost may not be that high, right? So there are other advantages as well. So agentic workflow is mostly studied for this particular aspect. And there are also cases where agentic workflows are very crucial, in the sense that like in some cases accuracy is of utmost importance, right? For example, banking sector, right? You can't afford to have less accuracy in that if you design a bot for making transactions, right? So in those cases, you can push the boundaries of what the models can do by building agentic solutions rather than directly using what the LLM gives you out of the box, right? So with that in mind, let's look at what were the initial papers that sort of helped us understand these advantages of agentic solutions, right? So these are very initial papers in this domain. Now things have evolved a lot, but let's go through these papers to understand how these benefit, right? So just like how human eval helped us understand the benefit of agentic versus non-agentic, there is also another dataset that's popularly used. It's a QA dataset, and it's called hotpot QA. This is a multi-hop reasoning data set. What it means is that look at the question, right? To what team was the 2014 NBA Rookie of the Year traded in October 2016? Right. So here, and the answer is Chicago Bulls. So if you have to answer this question, right, and let's say that you don't know anything about basketball or NBA to begin with, so how would you go about answering this question? Let's say I give you access to the internet. So how would you like use internet to answer this question?
Check the most reliable source.
Right. So how would you query the search engine?
First, search for the QPS. Okay.
Right.
Then look for its tag button.
Makes sense. So if you directly post this question on the web, it's very unlikely that you will get a good hit, right? Because the question is a little complex, and typically there may not exist any pages on the internet that will directly answer this question. So like he said, the best idea is to split this question into multiple parts, and then based on the output of the first question, you rephrase the second question, and then figure out how to use that question, and then look at the results and figure out what the answer is, right? So that's exactly how this data set was designed. So the information that's necessary to answer these questions comes from two different documents in the indexed RAG corpus, right? So you will have to first figure out the document about Michael Carter Williams. So basically, if you search who's a rookie of the year 2014, you're very likely to hit this particular document because of the phrasing here. And with this document, you will be able to figure out that Michael Carter Williams was the person who was awarded the Rookie of the Year. And although here it also has additional information, like he has also played for Milwaukee Bucks and Chicago Bulls. But if you don't know the answer, you may not be able to pick which of these two teams was the team that he was traded on. So what you would end up doing is that you will probably search for October 2016 trade and Michael Carter Williams in your second query. That will yield you to the next document, which is this one about the 2016-17 Chicago Bulls season information page on Wikipedia, where it clearly says that the Bulls traded Tony Snell to Milwaukee Bucks for Michael Carter on October 17, 2016, right? So this is a setup which helps us study agentic workflows better, right? Because if you directly post this to an LLM, right? Of course, LLMs will have the memory where they have all the information in their parameters. Wikipedia information would be there, but in addition to just remembering the facts, it should be able to reason that, okay, I need to get information from these two paragraphs of Wikipedia that I memorized, and I need to arrive at this answer. And of course, the other approach would be that if you have a corpus of these Wikipedia pages, then you may have a prompt which will divide the question into two parts. Right? You may have a prompt that will do a retrieval search, which will figure out what is the query that you should use for retrieval search for the first question. And then you get back the results, see what the results look like, decide whether you need more results or you're good with it. So this type of data set will actually help you study agentic workflows in a much more principled way, right? So there are also other benchmarks as well, like programming benchmarks is one such type. This QA is one. There is also something that people use for complex reasoning and other things. But for now, for most of our discussion here, we'll look into programming based tasks and hotpot and multi-hop reasoning data sets. So let's see how standard techniques work. So here, let's take this example, which is aside from Apple Remote, what other device can control the program Apple Remote was originally designed to interact with? Again, this is a multi-hop question. First, you will have to answer the question, what is the program for which Apple Remote was originally designed for? And then once you know the answer, then you need to figure out what other devices can control that particular program, and then give out the other option, right? So standard prompting is where this is the non-agentic workflow, where you give the question and then you let the LLM answer right away from its. In this situation, it is the memory, the parameters of the model itself, right? So the model comes back and says iPod, right, which is apparently not the right answer. And you might have also come across this particular technique called chain of thought. Again, this is also a non-agentic setup where rather than directly generating the answer, you reason what the answer should be with respect to the question, and then once you reason through it, then you arrive at the answer. Again, this is a non-agentic behavior. It's just that the reasoning will probably help the model to better uh, to better understand the problem and then correlate it to the solution at hand, right? So here it says Apple Remote was originally designed to interact with Apple TV. Apple TV can be controlled by iPhone, iPad, and iPod Touch. So most likely the part that went wrong is that Apple Remote was designed for Apple TV, right? So although it looks from based on a lot of information that the model has seen on the internet, TV might be the most like common program that remote controls, right? So it probably assumed that since Apple has a TV, Apple Remote would most likely be for Apple TV, and so but probably the part that Apple TV can be controlled by other Apple products could be true, right? So most likely the reasoning is reasonable, right? But it doesn't seem to arrive at the right answer. So in this situation, let's probably expose give LLMs access to a tool, right? And we say that okay, I have a corpus of Wikipedia pages. All these pages are indexed based on topic. So if you give me a search query, I can give you a list of Wikipedia pages that match the search query. If you give me a search query that exactly matches the title of the Wikipedia page, I'll give you a few sentences from it. Okay, so they designed the search tool that way. So here the model was first. So here what the model should do is first predict the search query and say that it in this example it has access to two actions. One is the search action and the other is the finish action. So in the search action, the parameter is what is the search query, and in the finish action, the parameter is what is the final answer, right? So based on the question, and since it has access to Wikipedia, it decides the first search query it wants to fire is Apple Remote. So it fired the query Apple Remote and it got some information about it. And from here, it understood that Apple Remote was originally designed for an application called Front Row, right? Which is correct. Now, it again searched for Front Row, but looks like there are no Wikipedia pages that corresponds to Front Row. It might have a few other variations of it. So the similar part will suggest the Wikipedia pages that are very close to the query Front Row. And so Front Row software gave out the right page. So it has access to some of these Front Row data, but finally for some reason the model was not able to arrive at the final answer. So at this point in time, it has the information necessary to arrive at the final answer, but for some reason it is unable to arrive at the final answer, right? So in this place, so this is an act only model, and in this setup for the Wikipedia corpus, they had given 3 different action spaces because you are defining what actions are. You're allowed to choose your action space however you want. This is just like designing an RL system, right? So when you design an RL system, you define the MDP by yourself. So you define what a state is, you define what an action is, and things like that, right? And the observation is something that you will get from the environment, right? That's how RL works, right? So in this setup is similar to RL. The state of the system is basically what you feed as input to the LLM, right? So that's the state of the system, and the action is what all is the LLM allowed to output. In this particular setup, the action is defined, the action space has 3 different actions. One is the search with a query, second is a lookup. So once you arrive at the page, typically Wikipedia pages are pretty long, so the when you execute the search query, only the first 5 lines or something comes up back to the LLM, right? So but if you want to search in that page, then you use this action called lookup, which says if you give me a keyword, I will get 2 lines above and 2 lines below the first match of that keyword. If you call it again, it will give you the next match, or it will say end of match or things like that, right? And finally, you are allowed to use the action finish, whose arguments is the final answer with which you will evaluate the system. So then what this particular paper proposes is that chain of thought, right, has excellent reasoning ability, right? It's not just jumping into answer right away. but it has an ability where it reasons with whatever information is presented to it and what information it has in its memory, and then it's able to do a good job on reasoning. So the for most reasoning related questions, it's doing a pretty good job. On the other hand, ACT only is very well grounded on facts, right? So because if you saw the chain of thought here, even though the reasoning was good, it was hallucinating that Apple TV was the program that was designed to use Apple remote, right? So in ACT only, it does a pretty good job in grounding itself to the corpus and not hallucinating. But the issue with ACT was that it was not able to reason properly, right? Because even though the answer might be in the front row page, maybe it didn't look up, it arrived at the answer very quickly, right? So they introduced this cycle of like tau, which is thought, action, and observation, right? So what they said is that once the user query is provided, the model has to first think through what it has to do. Like in this sense, it should think through based on the question and the context that I'm provided with, what is the best action at this particular point in time, right? So here it says that I need to search Apple remote and find the program it was originally designed to interact with, right? Which is obviously right, and it did right here too. It did right here too. Without thinking, it was able to get those right. Here too, it was able to get those right even after thinking. But in the fourth step, right, where the model said finish yes, here the model sort of goes back to the question at hand, which is this, right, and tries to understand, okay, what did I start with, right? Maybe typically what happens is like you start this tau, the action observation cycle. At some point in time, you lose track of what you started with, right? So reasoning gets lost at some point in time. So the good part about this thought process is that it helps you summarize things that you've done in the past in a nice way, so that the next action becomes a lot more intuitive, right? So here the thought says front row software is controlled by Apple remote or the keyboard function keys. So the answer is this, right? So it's able to get the information from the question and whatever output that it has got probably from this particular observation, and then it's able to think through it, and so the final answer is a lot more concrete here than the other approach, right? So these guys, in addition to Hotpot QA, also used another data set called Fever. So the task here is very simple, that you are provided with a fact. Like the fact could be Stranger Things is set in Bloomington, Indiana. Or the fact could be that Nicola Coster-Waldau worked with the Fox broadcasting company. So your goal is that you're provided with Wikipedia corpus, where there is information about people and entities that are mentioned here. So you are provided the same action space as what you had for Hotpot QA. So you search, you look up, and then finally you say whether this claim is supported by the corpus you have, or it is refutes, or there is not enough information to conclude that whether this supports or it refutes, right? So this is a similar task, and let's see how different techniques perform with this on these two data sets, right? So the way you measure performance on each data set is that for Hotpot QA, you measure exact match, right? So exact match is that if the answer is 3 words long, then your answer should also be 3 words long with those exact phrasing, right? And for Fever, it's simply accuracy, because you just have three classes of outputs. So whether the class match was right or wrong, right? So standard prompting is, so all these three are non-agentic solutions. You have standard chain of thought, and there is also a slight variation of chain of thought called chain of thought self-consistency. So this is simply, you set the temperature for inference to 0.7, you sample more than once, typically an odd number of times. In this particular paper, they sampled 21 times, and then they chose the answer which occurred the most number of times, right? So that is, so basically you are using the LLM more times than what you would, and because of this majority voting, you would end up getting better accuracies than just doing it once, right? So this is chain of thought self-consistency. Now the other variants are ACT, REACT. So this should be obvious for you, right? ACT is like you're provided with the action space that's given to you, and you give a few short examples in the prompt, and so the model should be able to follow those actions and then arrive at the answer. REACT is with thought, and so like I mentioned earlier, even with REACT, they found that chain of thought is still better at reasoning than React. Even though there is thought present in React, chain of thought was still doing a better job when it came to reasoning and then coming up with the right answer. So they tried two different back-off based approaches. So here the primary, so these are the two techniques in the bottom. So you start with chain of thought self-consistency, and out of 21, if none of the answers are more than 11 times, 11 or more times, then you back off to React. Right. So if you have high confidence on chain of thought self-consistency, you go for that. If you don't have high confidence, then you back off to React. Same with the other way. You do React first, and then you give it number of iterations it can try. Right. So say fix it to 5 or 7. Right. In 7 tau loops or 7 tau iterations, the model is not saying finish, then stop. Right. So if it is able to give you the finish action in less than 5 iterations or 5 iterations, you take the output of React. If it doesn't give you, then you back off to COT self-consistency, right? So here the conclusions are that React was always better than app, right? So it's good to always have thought. That is one conclusion you can make. And the second is, like I mentioned earlier, chain of thought is more likely to hallucinate than React, because React you can show where you got the information from, and so it's a lot more grounded and less likelihood to hallucinate. Of course, it's not like it has no likelihood of hallucination. It may still hallucinate when it generates the final answer, right? Even if it contains all the information. And of course, the other way around, React makes more reasoning errors than chain of thought, right? So there's a trade-off between React and chain of thought as well. And the most common issue is that it goes in this cycle of repeating the same action and thought, right? So because the history gets accumulated so high, right? So sometimes it goes into this loop of, it makes a mistake. Oh, to fix this mistake, I will correct it this way. That's also a mistake. So then it fixed that mistake, it goes back to the same previous mistake it makes, right? So it keeps going in cycles. So that is a very common issue that React has. And so people typically have this, in practice, people typically break off after these many iterations. If it doesn't give back the right thing, or I will see, like if it predicts the same action that it did before more than twice, then I will stop doing React, right? And the other important part is React's success is in this setup of Hotpot QA and Fever. It is very much dependent on the search tool, but a generalized statement is React's success is dependent on how you define the action space, right? Because nobody told you that you should only use search, lookup, and finish, right? You can use whatever action space you want, right? So in general, when you design React, the design of action space is very crucial in determining the success of whether your approach is going to work for this data set or not, right? So let's now look at the correlation between size of the model and React and the other baselines, right? So let's look at this part of the graph first, right? Which is, it's just a prompting based approach. You're not going to fine tune the model, right? You take the model as is, and whatever we discuss now, we're just going to apply it here. So what it says is, smaller models are good at directly answering the question, right? So if you see the one in blue, which is the standard prompting, they are doing good. For some reason, smaller models for Hotpot QA is not doing good on COT, 8 billion model. But as you increase the size of the model, I think the model is better able to use COT and arrive at the answer. And also, like in most cases, the models have memorized Wikipedia, so the capacity also helps in recollecting the facts better. And if you see ACT, for 8 billion model, both ACT and React are super low compared to standard prompting techniques. But as and when the model sort of increases, it was hard to decipher what is going right and what is going wrong, because the trends were different for, there was not a monotonous increase, a monotonous decrease in trends. There were a lot of other factors, like your choice of action space, the ability to reason, how much model has memorized Wikipedia. So the data set was not so conducive to clearly draw a trend of what is happening, what is not happening. So most of these results are not so conclusive. But the part is that it sort of looks like React by itself is not able to beat COT, right? So that is a conclusion you can draw from this and from the previous table as well, right? But on the other hand, what is interesting is that if you're allowed to fine tune, right, for this data set, you know all the successful trajectories, like for things that match the answers, you know the trajectory is right, right? And then if you fine tune the model using those, it is clear that React and ACT are better than COT based training, right? So this was a very good insight from the paper. So if you had other benchmarks or other use cases where the answer cannot come from the model's own memory, right, then it's very likely that React and ACT would be better than COT, right? So this was a conclusion from this. So let's take one such example where the answer cannot simply come from the model's internal memory, right? So one such agentic workflow or one such task that got extremely popular was something called SWE bench, software engineering benchmark. So what this benchmark has is that they've crawled 12 different Python-based GitHub repositories, and they did a lot of filtering to identify 2,294 GitHub issues associated with these 12 different repositories. So the issue may look like the data leak in GBDT due to warm start, and then it describes the whole issue, which is the first post of the GitHub, right, issue. And then it is also provided with the entire code base, right, the entire code base of where this issue was reported, right? So you take the commit before when the issue was reported, and then you take that particular commit and that represents your code base, right? So the code base is not same for all issues within that particular repo, right? And then the goal is for a language model to create a pull request for this particular issue, right? And they already have designed unit test cases, which are some unit test cases are specific for the issue that is and associated with the issue that is provided here, okay? And some of these test cases in general were passing, and they were associated with the code base, all the features associated with the code base here, right? So the goal is once if your PR is good and accurate, if the new test cases are all passing and the old test cases are also passing, like it should not happen that the new test cases are passing but the old ones are getting screwed up, right? So this is the entire benchmark, and of course the obvious issue here is that you won't be able to fit the entire input into the LLM's prompt, right? So this is a pretty big code base, and it is almost impossible for you to fit the entire code base into the prompt. So based on whatever you've studied so far, how would you design a solution for this particular problem at hand? So how do you, that's a good point. So you localize the problem so that you reduce the size of the prompt. So how would you localize the problem?
We did previous pull request that were successfully not able to what they can get, what the issue was and what were the five changes corresponding to that.
So you're saying maybe we could create a training data using previous PRs and the edits that were made for the pull request that was created for that commit, and then use that to fine tune a language model, which can, sorry?
Could be.
Yeah, that could be a way. Of course, that is a good way to synthesize data. So let's say that you don't have the luxury to fine tune a model. If that is the case, what would be an obvious solution? So how would you reduce the size of the code base? You probably would pick a subset of it rather than the entire set. That's your solution, right? So how would you pick a subset given that you have the issue at hand? Issue is always provided to you, right? So once you have issues, how would you select a subset of the code base based on the issue?
Create indexes of files and maybe the reason and map corresponding indexes with my
Right.
deeper into.
Makes sense. So one easy approach is index the code. Maybe just by searching using the issue, you may get some hits. Maybe you can look at those and then figure out whether it will help me solve the problem, whether this problem defined is sort of associated with this code base or not, and you can sort of iteratively get to what you want, right? So yes, you're right. So the obvious first solution is that you do RAG, right? You don't define any action space or anything, just say RAG, I will take the top K documents and then I'll see whether the documents, based on the retrieved documents, I'll provide what should be my PR, right? So that is typically the first solution, and that was a solution that was proposed as baseline as well. But now that you know React, right? Now that you know React, do you think just looking at the retrieved code base would always be right? If you retrieve top K code snippets from this library based on the issue, right? Because people typically talk about the surface form of the issue, right? Most people who raise the issue are not developers in the repo, right? They are users of the repo, right? And so they will only talk about surface level problem, like what they saw when they ran the code. They won't say what code to edit or which object is throwing an exception and things like that. Maybe they'll paste the error trace, and most likely if the error trace is pointing you to the right code base, that will be an easy way to narrow down, okay, if the error trace is mentioned in the GitHub issue, then it's fairly obvious to figure out where the issue is going wrong. But still, you may not be retrieving all the relevant places from where the error propagated and came to this particular line, right? So it looks like some sort of iteration is needed, right? To figure out, to see the issue, look at the first place where the error was made, and then sort of iteratively run over multiple parts of the code base, figure out. So now that you know React, what do you think should be the action space associated with this particular problem at hand? So as a developer, like you might have also had encountered similar things, right? You might be coding and then you think that you've done everything good, and then you start running the code. So now when the code throws an error, what is the first thing you would do? Locate which line the error got thrown. After that, what would you do?
Try to move that line
Huh.
and find out the particular function or particular call that is causing there.
Mm-hmm.
We try to alter the input, maybe try to see if the input is wrong.
Right. So you start to backtrack from the point wherein you know the failure happened for sure, and then you keep on backtracking until the point you figure out where the issue happened, right? So if you're using a debugger, then backtracking is not that difficult a problem, right? You can go back. If you have executed the code, you know the control flow, right? So you know the control to this function at this point in time came from that code. But when you're provided with a GitHub issue, you won't know the control flow, right? So if you figure out that it went till the top of the function, and now you need to know from where this function got called, then you would need access to the other code bases, right? So typically, what all would you do? You will need access to search. If I give you a function name, you should be able to search in the code base and tell me where all was this function called, right? Or if it is a inline function, then you will know where was this function defined, right? You need ability to search and browse through. So whatever you do visually or using command line tools or using your mouse pointer, you should be able to provide the LLM with all those actions. Ability to read, ability to scroll up and down the page, view, search, like all these actions that you do in an IDE should be the action space defined for SWE-bench, right? So there's this paper called SWE agent, which defined an LLM-friendly commands. Okay, so I'll talk about why do they call it LLM friendly, but in general the tools were related to navigating within the repo, searching for files, viewing files, scrolling files, and then finally you will have to propose a patch, right, or a commit. So for that you will have to say from this line to this line in this particular file, I want you to replace with what I give you now, right? So that is edit lines, and once you do all those changes, they say that it's good for my agentic or the agentic workflow to have access to a computer that runs the code that I give it, and then given that it has test cases, it should be able to run those test cases, give it feedback, and the feedback again will be passed to the LLM, and then this loop sort of continues. Okay. So how will the prompt look like? The prompt will first look like it will describe the entire what you're trying to build. Like if you're building a SWE agent, you will describe what the SWE agent is supposed to do, that you're an expert coder, you can do this, that, and you will also talk about, since it's a React agent, you'll talk about all the action space that you're allowed to do and how to use them, right? And then in addition to that, you will also have to give some few short examples, right? So this is a system prompt which describes the problem and the action space and what the output should be like, and then you will have some few short examples, right, which are successful, of course not failures, and then you will give the current GitHub issue and some more instructions along with it, and then you will go through the React cycles, which is start, action, and the observation would be that after you execute, what output came back and how you feed it back into the LLM, right? And then you will continue doing that until a point where the model would say that that I'm done, right? One of the action would be that I'm done, and when it says I'm done, it will pick all the edit commands or actions that were proposed throughout the trajectory, and then it will provide all those bundle all of them and then create a commit pull request, right? So let's see what all. So these guys define these particular actions, and now I'll discuss why this is LLM friendly, right? So let's say that some of the code snippets that you have may be too long, right? And when you provide such a long context into the LLM, it's not likely that it's going to pay clear attention to everything that is present there, right? There is always this problem with long context, that the model has a bias towards certain tokens that are in the extremities and not in the middle, right? So to counter for all those, and similarly there are other issues as well. So to make it more LLM friendly, they propose that you can open a file, and when you open a file, it only will display like 100 lines from the first 100 lines, right? And then you are provided the ability to scroll down or scroll up. So you look at that line, and then you say scroll down, scroll up. Then when you scroll down, then it will only give the next 100 lines, and it will say like, and then you also have the ability to go to a certain line, jump to it given the line number, and then the other things that I said, like how you typically debug, right? You'll be allowed to search a file, search within a particular directory, find the location of a file and things like that. And of course, these are for creating the PR, which is like you will say that you're going to edit line number X to line number Y, and then replace that with this particular blob of code snippet. And then you should also say end of edit, like I'm done with everything now, I'm done with solving the issue, now go ahead and then solving this particular edit, and then create. Of course, not always you will create, sometimes you will have to create a new file to write your own function and then copy it somewhere else. And then finally you're saying that I'm completely done with solving the whole task, and now you take all the edits that I've completed and then create a pull request, right? So these are some examples of how the action and the observation looks like, right? So one of the action is open file name, which is now it says open atmosphere.py, and then when it opens, it sort of hides the first 255 lines, gives the next 100 lines, and then says there are 180 more lines below. So because that these two lines, they have found it to be helpful to scroll up and down, right? Because sometimes you don't know whether you want to go through all the function definitions and you want to know where the main function lies and things like that. So this line numbering is helpful, and the numbering of the line is also very important because the edit action uses it very extensively, right? So you see the most important part in making React work is how you define the action space and how you define the observation, right? Because all this is in your control, right? So the design of this particular SWE agent would have gone through multiple iterations before they settle down, like, okay, I need this information to be present here, I need this information to be present here, I always need line numbers here, and all the other details, right? So these are some of the other examples of actions and their corresponding outputs, and this is how an example of the action for an edit looks like. You would say that you are already in a certain file in your previous action, and then you would say I want to edit line number 404 to 407, and this is the content that I want to put in, and then you also say end of edit. Okay. So here, so SWE bench is a 2,200 odd examples that I talked about. They also have a version of a subset of SWE bench called SWE bench Lite, which is 300 examples. So the cost associated with running these experiments is slightly lesser. So people do a lot of aberrations on SWE bench Lite, but report final results on SWE bench. So RAG setup is one approach where you just retrieve relevant code snippets and then provide them as input, and you see the percentage of issues that got resolved is only 1.31. But at that point in time, when they used this particular action setup and React, they were able to achieve 12.47 using SWE agent setup. And this particular aberrations on SWE bench Lite shows you if you chose whatever commands your shell allows you to do as the action space, what would you end up getting, right? So providing actions helps in so RAG only has one action, which is search, right? So if you provide a lot of shell based actions like ls, cat, and other things like that, then you will be able to achieve better numbers. So which means like if you know the right actions for your agentic workflow, then giving LLM access to all those actions would help it get better accuracy. And the next aberration between shell only and SWE agent shows that if you chose your actions more carefully, then you would still be able to improve your system, right? So this is the takeaway from the SWE agent paper. So yeah, so to conclude, React is reasoning plus act to arrive at the final answer. So the first paper that proposed React, it was slightly confusing whether it is the React that is helping, or it is the model's inherent reasoning ability that is helping, or how do we combine them and things like that. But it became slowly more and more clear that if the information necessary to solve the problem is not within the LLM memory, then React is always better, right? And you'll have to put a lot of effort into figuring out what is the right action space for your task at hand to get better solutions, right? Now, so far we've been more focused towards actions, and in the last lecture we talked a lot about external tools, right? So after these two lectures, it should sort of come to you that you can also use React framework when you have external tools, right? So where would that help? Typically, where would that help is, let's say when you make an external tool call, your arguments failed, right? And then the error message, when you fire the query and then get back, maybe you won't get success, you would get a failure, and the failure would have a message associated with it, so that will go in observation. Again, you will ask the model to think, it will say, oh, I saw the error message, this parameter was incorrect, so probably based on this feedback, I'm going to change this parameter to this value, and then it will run it again, right? So typically in the current like in the current time frame, almost everybody who designs tool calling with LLMs typically end up using the React framework. So now let's go to another a very interesting paper called Self-Refine. So the idea is fairly simple, right? It is that in case of React, you divided the problem into multiple steps, right? And then these multiple steps are grounded on the action space, right? You have a certain action space, and you traverse the action space in a certain trajectory, and you arrive at the final output. Now, this is a slightly different scenario where you arrive at the output, there's no action, anything necessary. You just arrive at the output however you want. Do straight, direct, standard prompting, use chain of thought, use React, use act only, it doesn't matter. You arrive at the final answer, and you ask the LLM whether, do you think this final answer is good or not, right? So you give the model the input, get the output, and then ask the output to provide feedback on the answer, right? Of course, this feedback is subjective. You can design the feedback prompt however you want, but the feedback the model will act as an evaluator and will give you the feedback, right? In the first case, the model acted as a generator. I'm going to give you the output for the task that you gave me. In the feedback setup, it will tell you okay, as an evaluator, I feel the solution is not so great, something is wrong here, maybe you can fix this and make it better, right? A nudge in the sense?
So if the LLM gives that the output is not output, does it matter?
Yes, so that's a refine step. So refine step says that I'll take the feedback, I'll take whatever output that I previously generated for this input, and now I'll refine my answer again.
How do you find this?
So we'll come to that, right? So this loop will keep continuing until the evaluator who gives you feedback says I'm good, right? Or the evaluator says like, or we give it a hard stop saying don't go more than 100 times, right? Otherwise it's too expensive. You're not able to get to the solution by 100 times, then stop, right? And give whatever you currently have. So they have let's see two examples here, one for code optimization and the other for dialogue response generation, right? So the user says I'm interested in playing table tennis, and the model generates, I'm sure it's a great way to socialize, stay active, right? This is what the model output gave. Now you have a feedback or an evaluator for which you create a separate prompt and say, look, you look at the response and you tell me along two dimensions, engaging and user understanding, about what you feel about this response, right? So now the LLM feedback gives a feedback, the evaluator gives a feedback saying, in engaging, it provides no information about table tennis or how to play it. And user understanding, it says, lacks understanding of users' needs or state of mind, right? So now it takes this particular feedback and the dialogue that has been, the entire trajectory that has been going through so far, and then it says that that's great to hear, it's a fun sport requiring quick reflexes and good hand-eye coordination, have you played before or are you looking to learn, right? So this part is making it engaging, because the moment you pose the follow-up question, then the user is forced to answer, right? So it creates a more engaging conversation. And secondly, user understanding also, it says that it helps it understand slightly better, right? Same thing goes with code optimization. You generate the code. So here, in your evaluator, you can also say that when you generate the code, make sure that the code has the best time complexity, or things like that, right? So then here model says that for this particular generating sum of n numbers, the code is slow as it uses brute force. A better approach is to use the formula directly, right, for first n natural numbers. So then the refined code would then look like this, which is a bit better along the dimensions that you wanted it to get better, right? So this is the algorithm. You will to start with, you will need three different prompts. One prompt is to generate the output at time step 0, which is you get the input. You need a task specification prompt that generates the output. Second is you need a prompt for giving feedback, and third is you need a prompt that will take whatever trajectories have been generated so far, incorporate the feedback, and then give you a refined answer, right? You need three prompts. So at step 0, you will use the model with the generation prompt and the input to get the initial output, and then you will iterate over it. So here, in this particular algorithm, what they have done is, I will get the feedback from the feedback model based on the input and the latest output, right? Using the feedback prompt, and using the feedback prompt or the time step I am in, I will decide the stopping criteria, right? If the feedback doesn't give anything good, or if let's say t is 100 or something like that, then you would stop. Then if not, then when you generate the next output, typically for refine, you give all the failures and feedbacks you've done so far, right? So this is very important here. For evaluating, you just need the latest output, right? But when you create a refined output, it's very important that you give all the outputs that you've generated, because the latest feedback that you have is only on the last prompt, right? So otherwise it may go in circles. You say that engaging is good, but informativeness is bad or something like that. Then maybe in the previous iteration, informativeness was good and engagement was bad, right? So if you give all of those together, then the model will be able to not make the previous mistakes it made again, and then arrive at a better solution. So it's important that in refine, you'll have to give the whole thing. So these guys evaluated on a bunch of tasks, right? Because this technique is in a slightly different dimension than React, right? So it has so they sort of showcased it in scenarios where even tools are not needed, right? So there are a lot of such examples. and so math, reasoning, acronym generation, dialogue response. So in most of the cases, what they see is that self-refined is at least as good as LLM or much better than LLMs, right? So this is a very important part, because here what they say is that as you increase the number of iterations you let the model to loop through, right? You always see monotonic increase in accuracy, right? Maybe in the first iteration you get a pretty good jump, and in the second iteration you may get slightly lesser jump and so on. But the good part is that it's okay to set your criteria to stop based on some initial analysis, right? You can sort of use this this sort of table to, or this graph to understand your cost benefit ratio, right? So let's say that you've got 5-point jump in constraint generation, right? Oh, sorry, code optimization, and then you only get 0.9 after that. Then maybe you can decide, I'll just let it do once, right? Because I'm not getting much by spending more money or things like that. So you can so this graph says that it's monotonically increasing, so you can decide your cost to benefit ratio and then decide accordingly. So now we saw self-refine, which is also another way of agentic workflow, and of course you can combine this with React as well, right? Because whether you arrive at the final answer in one shot or you go through the entire tau loop is up to you. But the problem with using self-refine and tau loop together is that it's going to, many a times it will explode the amount of context you would have. Imagine doing SWE-bench with self-reflection and React, right? It's going to be insanely high. The model will lose track of what it is doing at some point in time. So in the last, I'll talk about reflection. This paper also came along similar time frame, but this sort of combines the both React and the sort of self-refine together, but they also split the part of evaluation and reflection. So in self-refine, there was one feedback prompt that was supposed to evaluate the output implicitly and provide feedback based on that, right? So the good thing this paper did was that they said there is no need for you to club both of them together, right? Maybe there are a lot of scenarios where you know whether the output is good or not. Maybe you don't know why it is bad, or if it is good, you're okay with it, there's no worries. But if it's bad, you may not know why it is bad, but there may be some heuristics or some external environment based reward that you could get that says whether the output is good or not, and self-refine doesn't let you for a way to leverage it. But this technique tells you that it doesn't matter whether you use rule or LLM heuristic to evaluate, or whether you use LLM itself to self-generate test cases and then run them in an environment and get back the results, or you assume that you're getting the reward from somewhere else altogether using a reward function that you typically use in RL setup, right? So it doesn't matter where you get, as long as you get some reward, which is a vector reward, then we will give out a framework with which you can improve it iteratively without having to actually fine-tune the model, right? So here you have three actors. So in the previous approach, also we had three actors, right? Three prompts, which is the initial task prompt, and then refine prompt, and then and feedback prompt, right? So there were two modules for output generation, which is task and refine, and there was one module for feedback. Here it's the other way around. You have two modules for feedback and one module for output generation. Okay, so NA is the actor model whose job is to generate the output, whether you give only the input or whether you give the input and all the other feedback and experience that you gave. Irrespective of that, there is only one prompt that is going to give you the output, and that is the actor model. And there is another model called evaluator. Now again, this evaluator need not necessarily be an LLM. Like, you can replace this evaluator using whatever heuristics or rules or any other technique you have to evaluate. And then you have a self-reflection model, MSR, which will, based on the output that you saw and based on the evaluation, it will try to reflect and say what you did wrong and how you should correct it, right, in the action space that you have. So these are the 3 LLM prompts you have. And so here they are equating the actor language model to an RL policy here. So they are using the notion of policy here. The policy parameters are 2 things. One is the model itself, whose weights are associated with it, and 2 is they have this experience memory, which is basically all the whatever feedback the self-reflection model gave, all of them are stored with some experience in that experience memory. And with the experience memory as input and the model weights, it should be able to predict the next output, right? So here the state of the system is whatever action and output you have generated, and you keep doing this action and output until you get the final answer, right? And the final so whatever intermediate, so this is before you arrive at the final answer, whatever action observation or thought action observation loop you're going, they're calling it, it's typically called a trajectory, and they are stored in the short-term memory. And once you figure out that, okay, now I finally arrived at the answer, and the entire trajectory is referred to like this, where it has IE steps, and once you have the final output, then the entire trajectory is fed into the evaluator, right? The entire trajectory tau is fed into the evaluator, and the evaluator will then tell you, the evaluator will give you a feedback, and that feedback along with some other details are provided to the self-reflection model, which will give you a text-based reflection, right? So the evaluator will only give you a positive or a negative reward or something like that, or if it is 0 to 1, then it could give you a reward 0 or 1 or 0 to 1 or things like that. And then the self-reflection model will take the trajectory, will also take the evaluator output, and it will give you a text reflection of what went right or what went wrong, right? And of course, the simple operation is like the memory will contain the whatever reflective text was provided, and then you keep repeating this loop similar to self-refine until the evaluator tells you that it's good, or you exceed certain number of iterations. And of course, the same thing is repeated. Again, you generate a new trajectory using the same. So now the policy will not. Typically when you do RL, the model weights get updated in the policy, but here it's only the memory that gets changed, right? Model remains the same. It's just the memory that gets appended with a lot of these reflective texts. And in the next iteration, then the MEM part will change, and so you will end up getting a different trajectory. And then again you evaluate it, again you do self-reflection, add it to the memory, and then keep repeating the cycle until the evaluator believes that it has done a good job, right? So what was so great about this paper, right? The simple concept, they introduced 2 simple concepts, right, in this setup. One is that there should exist a notion of memory, and there should be a memory management within an AI agent or an agentic workflow, right? And in this particular setup, they had used a lot of heuristics to design 2 different types of memories, right? And they also used some heuristics so they have evaluated on different tasks, and based on different tasks, they did certain different things. But what the community realized slowly was that it's good to have React and self-refine working together, right? And it's good to have a notion of memory, right? So like after this paper came out, after the self-refine React and reflection paper came out, the most popular agentic workflow building software is LangGraph, right? LangChain and then LangGraph, right? So LangGraph started to support most of these components in a ready-to-use manner, so that you can mix and match and then build your own agentic workflow in a much more principled manner, right? So these papers all set a very good tone of how problems should be solved, what are the components that are mostly reusable across multiple different action spaces. Of course, you have to define your own action space, but what is the right level of abstraction of how these land graphs should be designed and how most agentic applications should define, right? It's not just land graph. There are like a lot of startups and all major companies have their own agent building kits. So these papers set the tone for how things should be built, right? So here is the evaluation of different types of agentic and non-agentic workflows. COT only is the only non-agentic workflow they have, and what they show is like it doesn't matter how many ever times you iterate, it's still going to be almost the same, and it's somewhere close to a little above 0.3. And React, again, React depends on how you define the action space, right, and how you define the observation. So you should take this graph with a pinch of salt. But again, it sort of reflects on what we saw in the React paper, where if you only use React separately, then with whatever action space they define, then it's very close to COT. So that also makes sense, right? And COT, so when you use the reflection framework, to arrive at the output, you can either go to the tau cycle and interact with your environment, come back, or you can ditch the whole tau cycle and directly arrive at the answer and give it to the evaluator, right? So these are the two graphs for those two techniques. You use COT and you use React plus reflection. And of course, like as expected, React plus reflection is better than COT plus reflection. So here it is very clear that with the right agentic setup, React shows dominance, right? Because in this paper, in the React paper, that was not very evident, right? It felt like there's not much that COT that React is giving over COT, right? But now, if you design your agentic framework right, not necessarily the action space, use of memory, right, use of evaluators, use of refinement and things like that, then you could React has much more capability than COT, right? So again, you should take this graph again with a pinch of salt, mainly because the evaluator they used for this looks at the ground truth and says whether it's correct or not. It doesn't say what is the right answer, right? But it just says that whether the answer is right or not. So technically these two are not like comparable, right? Because you have this additional information. The evaluator looks at the ground truth and says whether it's correct or incorrect, 0 or 1. Right? So the evaluator has access to the ground truth. So the red and the blue line has slightly more information than the COT or the React only setup, right? But the premise is that if you have that information or some proxy or heuristic or rule-based thing that can tell you that whether the answer looks right or not, then you can benefit from React a lot more than what you would benefit from COT, right? These are some, you guys already know human eval, which is a coding benchmark. The languages, they're divided in based on the language, Rust and Python. And there is also another programming benchmark called most basic Python programming. There's also another benchmark. So here they say that if you use a simple standard prompting, this is the setup, this is what you get. And if you use the reflection framework, you get much better numbers. Again, in these cases, you assume that you have access to unit test cases. You assume that you have access to the compiler and the executor, which will execute, give you back the results, and that will be the evaluator. And then your the self-reflection model will look at the output and then define what the reflection should be and how the model should correct itself. Okay, so to summarize, we just saw three good papers that sort of set the tone for agentic workflow. And almost every paper that you will read now on agentic workflow will have some components from these 3 papers. All right, thank you.